minus 1, 1, 2. Question is whether this set is whether S is a basis for R4. Definitely we know that the basis, the dimension of R4 is equal to 4. That's a known thing. It's a standard thing. So definitely in a basis of R4 there must be 4 vectors. Here 2 vectors are given. So how can we expand this S up to a basis for R4? Let us take the linear combination of S. And linear combination of S will be alpha into 2, 3, 0, 0 plus beta into 5, minus 1, 1 and 2. So this is 2 alpha plus 5 beta, 3 alpha minus beta, beta and 2 beta. Now we have to take such a vector which belongs to R4 but not in the span of A. So consider a vector x3 such that this x3 belongs to R4 but this does not belongs to the span of S. So we have to find such vector which is not in the span of S and still it is in R4. Then definitely the set of this vector and x3 will be a linearly independent vector in R4. So again think of a very simple example. Take alpha is equal to 0 or take alpha is equal to 1 and beta is equal to 1. Then we will definitely get 7 here, alpha 1 and beta 1. So 2 here, beta 1 means here 1 and beta is 1, so that's why this will be 2. Now if we slightly change the coordinate of this one, because of beta is equal to 1, this is 1 and this is 2. But instead if we take 7, 2, 2 and 2, then definitely this vector will not be the part of span of S. And we can add this vector in this S1. Not only this, we can also add say 1, 0, 0, 0. This is a very simple vector. And definitely 1, 0, 0, 0 is not a part of span of S. Because if we take this 0, 0, 0, then because of that alpha and beta will be 0. And this is different. So 1, 0, 0, 0 is also not a part of this one. So if we add this vector to this one, then our extended S, say S dash like that, 2, 3, 0, 0, 5, minus 1, 1, 2 and the 1, 0, 0, 0. This is again linearly independent. Again question is, can span of S dash is equal to R4? If yes, then this will be basis. And if not, then if we can find any vector in R4 which is not in the span of S dash, then again we can add that vector into this one and we can check that the set is not linearly independent. Okay, now the span of S dash will be like this. If we take the linear combination of this one with alpha, beta and gamma, then we will have 2 alpha plus 5 beta plus gamma as a first coordinate, 3 alpha minus beta, then beta and 2 beta. This is the span of S dash. Again if we take alpha is equal to 0, beta is equal to 0, definitely this will be 0, 0, 0 and 0. But if I take 0, 0, 0 and 1, then this is 2 beta is equal to 1, then beta cannot be 0. That means this vector is not a part of S dash. So if we add this vector into this S dash, this set S dash, then again all 4 vectors will be linearly independent. So if we define S double dash as 2, 3 0 0, 5 minus 1 1 2, 1 0 0 0 and 0 0 0 1, then this is again a linearly independent set. And we know that the dimension of R4 is 4. So the basis of R4 must contain at most 4 vectors in any basis. And here these are 4. That means S4 will be the basis of R4. So hence this way we can extend any linearly independent set up to the basis of that vector space. Now, if V is a vector space and if U is any subspace of a vector space, then dimension of U will be always less than or equal to dimension of V. This is very simple, because consider if U is equal to a 0 space, then definitely dimension of U will be equal to 0. But if U is not a 0 space, then definitely x1 will be some vector which belongs to the subspace U. And if we can say the span of x1 is equal to U, then definitely the dimension of U is equal to 1. We are considering V is a vector space with, say, dimension n. So if we can expand the whole of U with only one vector x1, then definitely this is linearly independent and dimension of U is equal to 1. Suppose span of x1 is not equal to U. Then again, by previous method, we can find vector x2 in U except the span of x1. Then this vector, the set of vectors x1, x2 will be linearly independent. And if the span of x1 and x2 is equal to U, then dimension of U will be 2. Again, if this is not equal to U, then again we can find x3 in U except the span of x1, x2. Then definitely the set x1, x2, x3, this will be linearly independent. And if the span of x1, x2, x3 is equal to U, then dimension of U will be 3. Otherwise, we can proceed this way and we can find maximum n element x1, x2 up to xn such that dimension of U is equal to n. And in that case, this span must be equal to U because U is a subspace of V, and if x1, x2, xn can span the whole of V, it can definitely span V. In that case, U will be equal to V. So if U is a subspace of V and if U is equal to V, the dimension of U and dimension of V will be same. Otherwise, the dimension of U will be always less than the dimension of V. And now finally we will move on to the most important theorem, that is known as a modular law of a vector space. Or we can say it is a dimension theorem in a vector space. This is very important theorem. If we are given that U1 and U2 are subspaces of a finite dimensional vector space V, then the dimension of U1 plus U2 is always dimension of U1 plus dimension of u2 minus dimension u1 intersection u2. And this result is known as the modular law in a vector space or a dimension theorem. Okay. Here we know that u1, u2, u1 plus u2, u1 intersection u2, all these are subspaces of V. And that's why dimension of u1, dimension of u2, dimension of this, all are less than or equal to n. If dimension of, we are considering dimension of V is equal to n. Say the dimension of u1 is equal to m, dimension of u2 is equal to p. Say dimension of u1 intersection u2 is equal to k. Then we have to find the dimension of u1 plus u2 is equal to dimension of u1 plus dimension of u2 minus dimension of u1 intersection u2. Now we know that u1 intersection u2 is definitely a subspace of u1 as well as a subspace of u2. Therefore definitely the dimension of u1 intersection u2 will be less than or equal to m and will be less than or equal to p. Here we have taken that the dimension of u1 intersection u2 is equal to k. So let us consider b1 is equal to say x1, x2 up to xk be a basis of u1 intersection u2. Now we have known that we can, so definitely b1 is linearly independent in u1 as well as this b1 is also linearly independent in u2. So we can expand this b1 up to the basis of u1. Also we can expand this b1 up to the basis of u2. Now we know that the number of vectors in the basis of u1 must be m and number of vectors in the basis of u2 will be p. So we can add few vectors in b1 and reaching up to the m vector so that it can be a basis for b1. Say we are expanding b2 as x1, x2 up to xk. Now let us expand. We are adding vector yk plus 1, yk plus 2 up to ym so that this can be a basis for u1. In the same way, we can expand this b1 so that x1, x2, xk, these are the common vectors. Now let us expand this one. Say z k plus 1, z k plus 2 up to z p so that this can be a basis for u2. And using this two, now we are defining a set B as b1 union b3. That means this vectors x1, x2 up to xk, yk plus 1 up to ym and zk plus 1 up to zp. And we can easily prove that this span of B will be equal to u1 plus u2. This part is very simple, that because all these vectors are the vectors of u1 and u2, so the span of B is simply a subset of u1 plus u2, and we can easily show that any vector x belongs to u1 plus u2, then definitely this x belongs to the span of B2. And if x belongs to u1 plus u2, then definitely x can be written as u1 say y plus z, because it is in the form of u1 plus u2. In that case, y belongs to v1 and z belongs to u2. So this vector y can be expressed as a linear combination of bases of u1 and this can be expressed as a linear combination of this one. Combining these two, we can find the linear combination of all the vectors of B, and this will be definitely in the span of B. So we can say that this X means U1 plus U2 is also a subset of span of B1. And for linearly independence, we have to prove that this B is linearly independent. And for that, if we take linear combination of vectors of V like alpha 1 x1 up to alpha k xk plus beta k plus 1 y k plus 1 up to beta m y m plus gamma k plus 1 z k plus 1 up to gamma p z p is equal to theta, then we can write this as summation alpha I xi, and we can easily prove all this alpha 1 alpha k up to beta 1 to this, and these are equal to 0. All alpha i's are 0, all beta j's are 0, and all gamma k's are 0, and this is a linearly independent set. And that's why we can say that dimension of u1 plus u2 is equal to, this is m plus p minus k. This m is a dimension of u1 plus dimension of u2 minus dimension u1 intersection u2. We can take also example and we can verify this theorem also, how this theorem works.
તો અહીંયા અજયભાઈએ આપણને ખૂબ સારું વ્યાખ્યાન આપ્યું છે બેઝિસ અને ડાયમેન્શન ઉપર. આનો બહુ સારો ઉપયોગ થઈ શકે છે ગણિતની ઘણી બધી પ્રશાખાઓમાં પણ એનો